Welcome to MEM18018 Maintain Pneumatic System Components. These lectures are a supplement to your student workbook and other resources made available to you. If you haven't yet done so, download and read the participants' workbook before proceeding with this video. Student resources. You should all be well familiar with Moodle or Pmoodle by now. As you know, we do not advertise updates and additions, so make sure you visit the resource section regularly to keep up to date. Don't forget, Moodle's available on your favorite mobile device. You can download the apps from the Apple Store, Google, etc. If you don't have access to a desktop publishing program, LibreOffice is a good, free, stable alternative and is available on all major operating systems. A download link is available on Pmoodle in the resource section. If you have a Google account, you have access to Google Docs. Google Docs has all the main desktop publishing programs, spreadsheets, documents, slideshows, and you also get 15 gigabytes of cloud storage. There's also the paid cloud subscriptions. One, for example, is Office 365. Any Pertec documents referenced in this lecture are available on pConnect, and if you don't have access to pConnect, they're all mirrored on Pmoodle. All the components, hoses, adapters, etc., and pneumatic fittings are all referenced from the Pertec catalogues. Good reference materials, especially textbooks, are invaluable when referencing or learning a new skill. We recommend the Hydraulics and Pneumatics, a Technician's and Engineer's Guide, as a recommended textbook for this unit. The textbook can be purchased as a hard copy or electronic version. Again, details for purchasing and downloading are available on Pmoodle. Apart from textbooks, other tools like software programs are invaluable for getting the job done efficiently and professionally. Pertec has partnered up with SMC to provide quality pneumatic components. They also provide a free pneumatic circuit design and analysis program. It's well supported and relatively easy to use. The download link for SMC Draw is also available on Pmoodle. Another alternative is the Bosch Pneumatic and Hydraulic Design and Analysis program. It is also free and includes hydraulic circuits. Pause the video now to record the download link or visit Pmoodle. Festo do a great design and simulation package. It's not free, but you can download a demo version. The download link's on the screen and available on Pmoodle. The Fluid Sim program enables simulation of circuits. Quite handy if you're doing complex circuitry. Or if you just want to visualize what's going on in a circuit. And there's always LibreCAD. You can create all the hydraulic components, save them as blocks, and then drag and drop them onto your desktop and create a circuit that way. Whatever tool, process, or reference we use, it's very important to apply the Work Smart method. This means we think, plan, do, review. Think, what am I doing? Plan, what do I need? In what order will I be performing these tasks? Do, execute my plan. Review, was I successful? Can I do something a bit differently? What went wrong? Main lecture. This lecture will be divided up into 5 sections. Section 1, first we're going to do some revision on fluid power. Section 2, then we're going to have a look at an introduction to pneumatics and pneumatic tools and systems. Then we're going to have a look at simple pneumatic circuits and the components and how to identify them. Then we're going to look at reading and debugging pneumatic circuit diagrams. And finally, we're going to look at maintaining pneumatic devices and equipment. Section 1, Fluid Power. Let's do some revision. What is fluid power? Fluid power is the use of fluids under pressure. This includes gases to do work. Hydraulic or pneumatic? Which one do I use? And what's the main difference? Hydraulic systems are used when high forces are required. But remember, in physics there's no free lunch. The high forces come at a cost: speed. Pneumatic systems are used for relatively low forces, but again, the advantage is that we achieve higher speeds. Liquids are almost incompressible. This is why they're able to consistently deliver more pressure over a certain surface area than a gas. What that means is a pneumatic cylinder has to be many times larger than a hydraulic cylinder to deliver the same force. What is the relationship between piston diameter or surface area of a piston and force? And why is it so important in pneumatics and hydraulics? Let's look at a simple example. Your lungs exert about 8 bar of pressure, approximately. That's about 8 atmospheres, to blow up a balloon. If the pressure from your lungs is not increasing while you're blowing up the balloon, why does the balloon get easier to enlarge as it gets bigger? Pause the video now. Have a think about it before proceeding. As we blow up the balloon, the surface area inside the balloon increases, thus giving the pressure more surface area to act upon, thus increasing our mechanical advantage. That's why if we increase the size of a piston, but leave the pressure the same, we'll be able to exert more force for the same amount of pressure. Remember, there's no free lunch in physics. Even though the balloon is getting easier to blow up, it's going to take longer to get to the final size. Let's have a look at a practical example of surface area and mechanical advantage. Here's the classic hydraulic jack diagram. In this example, we can see we're exerting a force of 50 kilos and we are able to lift 200 kilos. Therefore, I have a mechanical advantage of 4. And again, there's no free lunch in physics. That mechanical advantage came at a cost. Yes, it was the distance. The larger piston only moved a quarter of the distance the smaller piston moved. Mechanical advantage can be clearly visualized using the old classic lever diagram. The lifting ability increases, but the distance decreases. The law of conservation of energy states that energy can neither be created or destroyed, only converted from one form of energy to another. Think about when you put petrol in your car. As you're running your car, the energy is not being destroyed. It's just being converted into something else, like kinetic energy, heat energy, chemical energy. It's just being transformed from one form to another. It was neither destroyed or created. In relation to fluid power, it's important to remember that calculations are based on surface area of a piston, not the diameter. The SI unit for surface area is meters squared. A commonly used unit is centimeters squared. Let's quickly review the relationship of surface area, pressure, and mechanical advantage. For convenience, we'll be using the derived units of kilograms for force, bar for pressure, and we'll specify surface areas in centimeters squared. Pistons will usually be specified as a diameter, so we'll need to convert that diameter into surface area. We use the pi r squared formula to convert diameters to surface area. Our force pressure area formula requires centimeters squared, so we'll convert the cubic millimeters to cubic centimeters. By dividing the surface area of the larger piston by the surface area of the smaller piston, we got the mechanical advantage, which is 4. Let's look at the pressure exerted on the large piston. Let's use our force pressure area triangle, and let's make pressure the subject of the formula. Pressure equals force divided by area, so pressure equals 200 kilograms of force divided by the surface area of the large piston gives us a pressure of 10.2 bar. If you need that in SI units, that's about 1,000,000 pascals, or 1 megapascal. A lot of componentry and circuit diagrams for hydraulic and pneumatic systems are very similar. Here's an example of a hydraulic circuit. Here we can see the directional control valve allowing hydraulic fluid to flow into the back of the cylinder, extending the rod. We can see in the diagram the hydraulic oil leaving the front of the cylinder is being returned to the oil reservoir. Here is the same device using compressed air to extend the cylinder. In this case, the exhaust air is not returned to the reservoir or the storage tank, it is released to the atmosphere. Pressure and flow rate in a pneumatic and hydraulic circuit. They are both totally independent phenomena that work together to enable us to do work. Look at a nut and bolt. They're both different. By themselves, they are useless, but together they can do work, like bolting things together. Pressure and flow rate have the same relationship. Independently, they are useless, but together they can perform work, exert a force, move something, for example. Let's memorize the following. Pressure equals force. Memorize this also. Flow rate equals movement. Hydraulic and pneumatic systems use a combination of pressure and flow rate to do work. There is no point being able to move 1,000 kilograms nowhere. And there's no point also in moving no weight at 100 meters per minute. So we need flow rate and pressure to be able to do work. Let's have a closer look at pressure. Ever wondered why a pressure cleaner can generate so much force and not use much water? Pressure is resistance to flow. Look at the diagram of the fluid conductor. We have 200 liters a minute of material moving through that conductor. Look at the pressure gauges, they're all reading 0. Remember, pressure and flow rate are two distinct phenomena. We can see here we've got 200 liters a minute and no pressure. As a side note, those gauges would read a little bit of pressure because we've got friction between the material and the walls of the conductors. Every time we hit a bend or a change in diameter of a conductor, we're going to get a bit of turbulence, therefore we're going to generate some friction and pressure. At a later unit, when we look at designing pneumatic and hydraulic systems, we'll have to take into account friction and efficiency factors in fluid conductor assemblies and equipment. Let's provide some resistance to flow. Let's bolt a cylinder on the end of our fluid conductor. Now we have pressure in our circuit because we have resistance to flow. Have a look at the narrower section of our fluid conductor. The pressure is considerably lower than the larger diameter fluid conductors. The pressure's dropped in the narrower section of the fluid conductor, but look at the flow velocity, it's increased. That 200 litres a minute flow rate needs to maintain throughout the whole fluid conductor. Therefore, if it encounters a narrower section, the fluid needs to increase in velocity to be able to move 200 litres a minute through that narrower section. This is why it's very important to select the correct hose bore diameter, hence the cross-section area, to reduce heat and excessive wear. Remember, pressure is resistance to flow. Look at our force pressure area formula. Flow rate nowhere to be seen in that calculation. Now let's look at flow rate. Jogging your memory, remember, flow rate equals movement. You're probably already aware that flow velocity and flow rate are two different phenomena inside a hydraulic and pneumatic circuit. We take flow velocity into account when we're selecting hose cross-section areas for hose assemblies. It's basically based on how fast an oil molecule moves from A to B. These molecules rub against each other and rub against the hose, creating heat. And this is where the problems of incorrect hose sizing can cause problems. Flow rate is basically how fast a quantity of oil moves in a circuit from A to B. This is what's in charge of movement and the speed of movement in a hydraulic circuit. Let's return to our fluid conductor diagram. Here we can see, irrespective of the diameter of the conductor, the flow rate stays the same at 200 litres a minute. For the 200 litres a minute flow rate to be maintained through the narrow section, the flow velocity needs to increase. In the larger sections, the flow velocity is 3.2 meters per second. In a narrow section, it had to speed up to 5 meters a second to maintain the 200 litres a minute volumetric flow rate. Let's check your comprehension. What's determining the speed of the piston rod at the end of the fluid conductor? Is it the flow velocity or the flow rate? Pause the video now and have a think about it. If you selected flow rate for cylinder speed, you'd be correct. Let's look at our flow rate formula triangle. As we can see, pressure is not a factor in the calculation. An easy way to remember the relationship between flow rate and pressure: a weak shower means low flow rate, not low pressure. Section 2, Introduction to Pneumatics. The components described and referenced in the following slides are taken from the Pertec SMC Pneumatics product catalogue. The catalogues are available from Pertec website or from pMoodle. What is pneumatics? Pneumatics is the science of pressurized gas used to transmit force and energy. In plain English, pneumatics is used to do work. How do pneumatic machines or systems work? There are 5 basic elements to a pneumatic system. The first is a compressor. This consists of a pump and a motor which is used to collect and compress the gas or the air in our case. The second is a reservoir or receiver. This is used to store the compressed air or gas. The fourth are valves to direct and control the flow of the gas. We will also need a circuit, which is basically the tubing and the piping that moves the gas around the circuit. And finally, we'll need an actuator or a motor. This is the part that does the work. For example, a cylinder, an actuator, air, power tools are some examples. Let's have a look at the compressor. The compressor is made up of a pump and a motor. The rotating motor is connected to the pump, and this pump rotates and squeezes air taken from the atmosphere into a storage tank, which is used to do work. The motors driving the pump can be electric, petrol, diesel, or gas, to name a few. The power required to drive the pump will be determined by the volume of air that we need to move and the pressure that we need to achieve. The compressor pump. Remember, pressure is resistance to flow, so we'll need an efficient pump and a powerful motor if we're dealing with high pressures. Charts, tables, and apps for sizing compressors can be found on compressor manufacturers' websites and technical documentation. Types of pneumatic compressors. There are many types of pneumatic compressors depending on the application. Compressors can be divided into 2 distinct categories. Positive displacement compressors moves and compresses the gas by pushing it through a one-way valve, or a dynamic compressor moves and compresses the gas by accelerating it. Let's look at positive displacement type compressors. In this example, we're looking at a reciprocating type compressor, and this involves the movement of a piston of some type. Here we can see another type of displacement or positive displacement compressor, and this is a rotary type. This usually involves the squeezing of the gas between 2 rotating mechanical elements. Dynamic is the second main compressor type. This works by accelerating the gas or the air, then storing it under pressure in a reservoir. Pictured above is an actual flow compressor. The type of compressor you choose for your particular application will be determined by your specific requirements. Some examples: you might require a high flow or high pressure, or both. You might need efficiency or a unit that is quiet. The next main component of a compressor is the receiver or the reservoir. This is where the pump stores the compressed gas or air. Why do we need a reservoir? Gases are compressible. Therefore, we would not be able to get instantaneous power or movement if a pump was directly connected to an actuator. What we can do is pump the gas or air into a reservoir and store it under high pressure. This way, when the pressure is released from the reservoir, it is already in a compressed state, which will be able to provide us instantaneous power and instantaneous flow rate. Remember, flow rate is movement. In summary, using a reservoir provides us with near instant force as soon as the operating valve is opened. Don't forget, flow rate equals movement and pressure equals force. There are many terms and units associated with compressor units. One of the main terms that you'll need to be familiar with is the FAD, or the free air delivery rating for the particular compressor unit. This is usually quoted in litres per minute for SI units or metric units, or CFM, or cubic feet per minute, for the inches system. The next major component of a pneumatic system are the valves. The valves control the flow and the direction of the compressed gas or air. The direction or flow of compressed gas can be controlled manually, electrically, or pneumatically, or by other valves. We can use flow control valves to control the speed of a cylinder or an actuator. But remember the difference between flow rate and pressure. Although we can change the speed, the pressure or the force always stays the same. The next major component of a pneumatic system is the circuit. This consists of the conductors, or the tubes, pipes or hoses that move the compressed gas around the system. The compressed gases can be moved around the circuit using rigid or flexible conductors, like the blue tubing that we see on many pneumatic systems. Rigid conductors are available in plastic and metal. Flexible conductors are available in plastic. The final component of a pneumatic system is the actuator, or the part of the system that does the work. Compressed air can be used to drive motors. Compressed air can be used to control actuators. Positioners and pneumatic clamps are some examples of actuators. Pneumatic power tools are a common sight in manufacturing and maintenance. In this slide we can see a comparison between a pneumatic and electric angle grinder. In this example, the pneumatic angle grinder has the advantage of being able to achieve higher speeds, not damaged by stalling or overloading. It's lighter, it's tougher, and it's safe to use in wet environments and outside. The disadvantages of pneumatic power tools is that you need a compressor and an air delivery system in the area that you're working in. And pneumatic tools are not as readily available as electric tools. In conclusion, let's revise the 5 main components of a pneumatic system. The first is a compressor, and obviously a compressor and a motor. This collects and compresses the air. 2, we're going to need a receiver or a reservoir. This stores the compressed air for later use under high pressure. 3, we're going to need valves to control the direction and the flow of the compressed air or gas. We're going to need a circuit. We're going to need conductors, something to move the compressed air around the system. And finally, 5, we're going to need an actuator or a motor. This is the part of the pneumatic system that does work. Let's now look at simple pneumatic circuits. If you recall from year 1, one of our initiatives in sustaining an environmentally friendly workspace was to recycle aluminium cans. This is great, but having hundreds of aluminium cans lying around can take up a bit of space. Many of you suggested using a can crusher or crushing aluminium cans to save space so you could recycle more. Can crushers can be purchased or custom built using pneumatic or mechanical components. We will be studying the pneumatic circuit in a can crusher to familiarize ourselves with the operation of simple pneumatic circuits. Here we can see a commercially available can crusher in action. Note the operation as the operator removes his or her finger from the actuation button, the cylinder returns or retracts. Here we have an example of a very basic pneumatic circuit. We just apply compressed air to the extension port of the cylinder and the push rod extends. This is not very useful as there's no way to return the push rod back to the retract position. When designing, repairing or maintaining pneumatic circuits, we need to understand how the mechanism works and its purpose. Questions to ask. How does the mechanism work? How will I control the flow of compressed air? Is the mechanism completely operated by compressed air, or are there other energy sources involved like potential energy, springs, gravitational energy, weight, kinetic energy, movement? In the diagram we can see, even though the compressed air has been vented to the atmosphere, the push rod still has no way of returning to the retract position. In this diagram we can see that gravitational energy is used to return the cylinder to the retract position, obviously only when pressure is released from the extension port. In this diagram we're using a spring to retract the push rod. If we're going to automate the process, we will need an efficient way of moving compressed air around the circuit and venting compressed air to the atmosphere. Let's add a valve to our circuit. In pneumatics, this type of valve is called a directional control valve. Specifications: push button, 2-position, 3-port directional control valve. Let's first look at the positions. It's a push button switch. It has 2 positions, an on and an off position. The on position, when you press the button, feeds compressed air to the extension port and seals off the circuit to the atmosphere. The off position, when the button is released, cuts off the compressed air supply to the circuit and vents the extension port to the atmosphere. There are 3 ports on our directional control valve, or connection points. One port is for the supply of compressed air. Another port is the exhaust. This is sometimes fitted with a silencer or some flow control. And one port is the feeder to the extension port of the cylinder. Once the button is pressed, you can see the free path to the extension port of the cylinder. Take note, the exhaust port has been blocked off. When the button is released, we can see that the supply has been isolated and the air in the cylinder is free to escape into the atmosphere. As there is no longer any pressure in the cylinder, the spring returns the push rod to the retract position. Sometimes cans get jammed at the end of the stroke and the spring is not strong enough to retract the push rod. Let's fix this by using a double-acting cylinder and a 2-position 5-port directional control valve to drive the push rod in both directions. When the button is not pressed, air is fed to the retraction port, keeping the push rod in its retract or home position. When the button is pressed, compressed air is now diverted to the extender port. Note that the retract port is now vented to the atmosphere. Releasing the button will reverse the flow. When releasing the button, a spring returns the spool to the normally open position on the retract port. Pictured here is a description and positions of the components used in our can crusher example. Section 4. Reading pneumatic schematic diagrams. As with engineering drawings, there are standardized formats and symbols describing the components and their relationships between each other on pneumatic schematic diagrams. Here's the schematic diagram for our can crusher, utilizing the 5/2 directional control valve. Let's look at the basic symbols used in this diagram. Before we continue, here's a quick summary of some of the most commonly used pneumatic symbols. You can download your own copy from the resource section of Pmoodle. Let's start off by looking at cylinder types. We've already looked at a couple of types of cylinders or pneumatic cylinders: single acting spring return, and double acting. In our circuit, we will want to drive our cylinder in both directions, so we'll be selecting a double acting cylinder. As well as a symbol reference guide that you can download, here's an example of how I'm using the parts library in SMC Draw. In this example, I've drag and dropped a double acting cylinder into the workspace from the cylinder library. I'm not going to just grab any cylinder. I need to make sure that the cylinder is appropriate size and stroke for my application. I've done a bit of research, and it takes 81 kilograms of force to crush an empty drink can. Using the force pressure area triangle, I determined that I need a cylinder with a 63mm diameter or bore for use with my workshop compressor, which outputs 6.8 bar or 100 psi. The drink can is about 150 millimeters high, bit of clearance for my hand. Yes, let's select a stroke of 200 millimeters. A quick check on the Pertec Pneumatics catalog, and I've selected appropriate cylinder for my application. Let's add the part number of the cylinder to my schematic diagram. Now let's look at selecting a directional control valve. When I press the button, I'm going to need the cylinder to extend. When I release the button, I'm going to need the cylinder to retract. Let's collect some information. How is the valve actuated? Is there a button, a lever? In our case, it's a button. How is it returned to its initial position? Is there a spring? Is it manually returned? In our case, it's a spring. How many connection points will I need? Before we continue, it's important to remember that some manufacturers use numbers to identify ports and connection points, and some manufacturers use letters. Refer to the components data sheet for details. The next bit of information is how many positions does the valve have? This diagram displays the initial position, or position 1, before the button is pressed. Here we can see after the button's pressed, the new flow path for the compressed air. Pictured is a cross-section view of a 5/2 directional control valve. When the spool moves from left to right, it opens and seals specific ports to direct the flow of compressed air. Our particular flow control valve is push button operated, but directional control valves can be actuated by push buttons, solenoids, levers, and compressed air. Once again, I've located the appropriate directional control valve. I've dragged and dropped it into my SMC drawer workspace. A quick search through SMC catalogs. I've located the appropriate part number. Just a reminder that you can also get the part numbers from SMC Draw. I've used the catalog example just as an exercise. Let's add our directional control valve part number to our schematic diagram. Let's have a look at air supplies. As I'm not designing the air supply for this project, I'm using my shop compressor. I will use the existing air supply symbol in my schematic diagram. If I have specific air supply requirements for my circuit, I can detail components like lubricators, accumulators and dryers, etc. On the slide there's also an example of a maintenance unit and lubrication system made up of individual components for air preparation. We will look at air preparation and maintenance issues in the next section of this lecture. Let's detail our supply requirements on our schematic diagram. My exhaust ports. Am I exhausting to the atmosphere? Do I want to fit any silencers, for example? Other components that I can fit on the exhaust ports are exhaust and throttle units, silencers, throttle and silencer units. Let's have a closer look. If you remember from our basic fluids theory, flow rate equals movement. So if we control the flow rate, we control the movement and the speed of movement. In this example, the two circuits are identical. We can control the flow of compressed air at the cylinder ports or at the exhaust ports. The result is the same. Where the flow control valves are located is usually determined by the designer of the system and the physical limitations of the device that we're manufacturing. In our example, we're not too fussed about speed, so let's just fit a silencer on our system so we don't annoy our workmates. Let's add the silencer part number to our schematic diagram. Here's an example how I utilized Fluid Sim to check my circuit for operation. Here's a couple of snapshots from the video. We can see the position of the valve and the push rod when the button is pressed and when the button is released. I've just completed a risk assessment for our can crusher and realized there's a serious crush or amputation risk associated with using the can crusher. My control measure on my risk assessment will be to add an extra button and force the operator to use two hands or press two buttons at the same time to actuate the crusher or the cylinder. I'm going to need a few extra parts. I'm going to need an AND valve. I'm going to need a pilot or air activated 5-port 2-position spring return control valve, and I'm going to need two 3-port 2-position spring return valves. Before I order any parts, let me simulate my circuit, make sure I haven't forgotten anything or it's working properly. When buttons A and B are pressed at the same time, the solenoid C is activated, thus extending the pushrod. If either buttons A or B or both buttons are released, solenoid C is deactivated, returning it to its initial position by the spring, and hence the pushrod is then retracted. Section 5. Maintaining pneumatic devices and equipment. Remember the trade method from Year 1? That's our approach to trade-related activities and tasks. Let's apply our trade method to the maintenance of pneumatic systems and components. Do you remember the 5 steps? Think, research, acquire, do, and evaluate. The first thing we do is think about what we're doing. Before we start any work, let's think about what we're about to do. Is there a service manual? Are there work instructions? Do I have access to the supplier? Do I know who the supplier is? Are there any old job sheets or service reports? Is it a return customer? Is that a clue? Do I know what I'm doing? Do I have the experience to do the job? Are there any hazards or risks that I need to address? But before we do anything, we're going to have to do a take 5. Take 5 comes in handy here, as it answers most of the questions I asked when I went through the think stage of the trade method. And of course, the take 5 will trigger a risk assessment if required. Here's an example of a service manual I got from a supplier's website. Here's an extract from one of our work instructions on maintaining our internal pneumatic system. Here we can see information on weekly, monthly, and 6-monthly service activities on our pneumatic system. This could also give us clues to any potential issues or problems that we're having. In this example, I've gone to SMC's website and I can extract detailed information on components. Here we've got a cross-section model of the parts contained in a pneumatic cylinder. Now that I've thought about what I'm going to do, let's now proceed to the research stage of my trade method. At the beginning of the lecture, we spent a bit of time looking at what pneumatics is and how it works, and the theory behind its operation, reading schematic diagrams, etc. It's very important to have an understanding, for example, of pneumatics before we attempt any maintenance or repairs on a system. While I'm researching, I might ask myself some questions. What is the part and what is the function? How does it work? Is the component serviceable or designed to be replaced? Are there standard parts or service kits available? What caused the problem? Did the component fail before its expected service life? Do I need any special tools or equipment to complete the job? Let's have a look at why pneumatic systems fail. So let's do some research. Components and lines clogged up with contaminants. The air supply could be contaminated. Contamination could be water, particles, rust particles. Is the filter clean? Is it working correctly? Pneumatic parts have been subject to corrosion. Is there any corrosion of components in the circuit which is causing contamination? Should I be using stainless steel components in my pneumatic circuit? Is the filter lubricator working correctly or being maintained correctly? Is the lubricator working? Is it injecting sufficient amount of lubricant into the system? Are components in the circuit rubbing metal to metal? Am I using the correct oil in my pneumatic circuit? Is the incorrect oil or the oil that I'm using corroding the seals and creating a bigger problem? Always use the oil or lubricant specified by the OEM component manufacturer. A good quality and well-maintained service unit is critical to maintain a reliable system. Make sure you're using the appropriate service unit as well as the correct lubricant. By connecting your pneumatic device to an incorrect air supply, you could be shortening the service life of your component or your system. And you could also void any warranty on your device. Operating out of spec. Make sure you've selected the correct component for the application. Remember, do your calculations. Springing a leak. All pneumatic systems will eventually leak from somewhere. Remember, air leaks cost money and waste energy. Another common problem is poor maintenance of pneumatic equipment. Look, at a minimum, you should base your maintenance schedule around a pneumatic component manufacturer's recommendation. There are heaps of apps and programs available for helping you create and maintain maintenance schedules. Some of the other common and useful questions in the research stage of our trade method are: what is it? How does it work? What's its history? Who uses it? Why is it used? How many would I need? What are the constraints? How long does it need to last? These questions also help us make decisions when we're maintaining or servicing or even designing a pneumatic system. The next step in our trade method is acquire. Some questions to ask yourself. Do replacement parts need to be manufactured or conform to a standard? Are parts readily available? Are aftermarket parts suitable for your application? Do I have the correct part number and identifiers for my component? Pneumatic part numbers can be a bit complicated. We need to check that. And what about lead times? How long does it take to get these parts? Here's an example of specific standards for an industry. Here we have the SMC's medical industry product catalogue, all components and parts certified to be used in a medical application. The next step in our trade method is the do, performing the task. Let's ask some questions. Am I following a work instruction? Are there any other work instructions affecting the job? For example, lockout and tag out, isolating a piece of equipment. Am I using the correct tools? And the last step in my trade method is evaluate. Was the job successful? Did anything go wrong? Or were there any unexpected complications? Could have anything been done differently to improve the outcome or speed it up? Did I complete all the documentation or any documentation? Do any tools need to be replaced, repaired or upgraded?